Okay, next problem. I should just keep rolling. So the question is, what's electric field right near the sheet, a thin sheet, near the middle? And it has, can't see. Okay, they give you the size, and they give you the total charge. But the important thing is that we could get the surface charge density. I'm sorry. It'd be the total charge over the area. So sigma is the charge per unit area on that sheet. That is important. Now you think, who cares about Gauss's law? No one cares about Gauss's law. You care about Gauss's law because it's a great trick to solve for problems like this. So if I have this, let's say it's positive. Now, and I infer something about the shape of the electric field, and I know that, let's say it's constant and pointing away everywhere. Like this. Okay. Because it has to be uniform once you're near the surface. There are edge effects, but don't worry about that. Now, let me see if I have another color. Now I can do, they call this a pillbox, and it's, I know it's dumb, hold on. But let's say I take a box, or it can be any shape, a cylinder like that. Can you see that? Yeah, okay. So, and this has some length L, it doesn't really matter, surface area A. In that case, I can calculate the total flux, and I can use that to find the electric field. So Gauss's law says that the total flux, I'm switching back to black, the total flux is going to be Q inside that box divided by epsilon naught. That's the total flux. Now, the total flux is complicated, so you only want to use it in situations that's easy to calculate. In this case, it is easy to calculate the total flux because on this side, all around there, the electric field's either straight up or straight down. So dA is that way. Those are the dAs, the area of the vector for the area vector. The angle between the electric field and that is what angle? Did you say pi over 2? That'd be correct. Also, an answer would be 90 degrees. Either of those are acceptable. Okay. So if I use the flux of E, A, or dA, cosine theta, and if theta is 90 degrees, 0. No flux on the side. Same thing, think of this as rain. Rain shooting out both ways and won't hit the side. Okay. So those have 0 flux. Now on the top, up here, what's the angle between the area and the electric field? It's 0 degrees. And the electric field's constant. So on the top up here, the electric flux is going to be equal to E times A. That's it. And then down here, it's also equal to E times A. So all the total flux is 0 plus EA plus EA. Notice that if the fields are pointing outward, that's a positive flux because of the way we define the angle. And I think this is positive charge. Yeah, positive charge. Okay, so that's the total flux, and I set that equal to, so it's going to be 2EA QN over epsilon naught. Now, all I need to do is find QN. But look right here. If this pillbox cuts the surface, it has a little section of size area A. I don't even care what the radius is. That area is A. And I can use that to calculate the charge there because I know the charge density. So if the area is A, this should be, let's call that AT. That's a total charge on the sheet, and that's the total area of the sheet. And that'll give me the density in coulombs per square meter. So now I can find, if I know this has an area A, then it will have, the total charge inside is going to be equal to A times sigma over epsilon naught. So if I put this all together, I get, the A's cancel. Let's write it up here. 2EA equals A sigma over epsilon naught. The A's cancel, which is good. It doesn't matter how big that pillbox is, because the bigger I make this, the more flux I have, but the more charge I have in there too. So for E, I get E equals sigma over 2 epsilon naught. And you're going to need to calculate that sigma based on the size of the plate and the charge. Okay. Now, there's a problem here that no one talks about, and that's using Gauss's law to solve electric fields. We assume something about the way the field looks first. We assume it's uniformly pointing out in all those directions. And then we use that to our advantage to find the magnitude of the force, of the electric field. And this could be still a function. It could change with distance or something like that. It happens to be constant. But we don't, this is not the electric field vector now. We have, if you wanted the vector, you'd have to go back and say, oh, I know it's in the up direction. Okay, so you don't really get the total electric field. You're just kind of getting the electric field. Okay, I'm going to look at another problem. Oh, part B. What is electric field 16 meters above the center of the sheet? Okay, so it's a 40 centimeter sheet. And now if I'm way up here, this looks like that. And I'm trying to find the electric field up here. So in that case, for part B, just assume, I would say, just assume it's a point charge, because it's a 40 centimeter sheet and you're like, 40 feet away. So it looks just like a point. So just use the equation for a point charge. E equals 1 over 4 pi epsilon naught Q total over R squared, and that gives you the magnitude, and that's 16 meters. Okay. Let's see, next one. Okay, these are fun. Okay, I'm going to do, this is one non-conducting sphere. The charge is over the shell. What's the electric field? Okay, I'm going to do this one, and then I might stop and let you work on these, because here's the deal. I mean, it's not about the answer. It's about working through these problems. And getting stuck is okay. I mean, that's part of the learning process. So I don't want to steal that getting stuck away from you. I think maybe if you do these, you might be able to get further on the other ones, but I don't want to just do them. I mean, I want to do them because I like physics. Okay, last one. I'm going to go quick. You can replay this in slow motion or fast motion or backwards or whatever you want. Okay, so we have this. Okay, is it a cylinder? Let's see, it's a sphere, and has charge Q, R1, R0. That's weird. Okay, they call this R1. They call this R0. And the total charge is Q. And we want to find the electric field between 0 and R1. Okay, that's easy. So I'll do two parts. So if I draw, the key is to imagine what that electric field would look like so that you can then go back and kind of make a Gaussian sphere. This is a Gaussian surface. Since this is a sphere, I'm going to pick a spherical surface. It's not real. Can you see that? I think you can see that. Is that better? It's not a real surface. It's just an imaginary surface. But if I do that, and I assume the electric field's spherically symmetric, then I can use Gauss's law. So what's the total charge inside that sphere? Well, there's none. So the flux has to be 0. If the flux is 0, then if I assume everything's spherical, then the only way that would work is if the total electric field is 0. So the electric field in this region is 0, because there's no charge in there. Okay, but now let's say I want to find the electric field in here. So this is a radius r. So I picked that because I'm assuming the electric field is going to be spherically symmetric. I don't want to pick a Gauss's law problem that has me actually integrate. I want to do it so easy so that I don't actually have to integrate, because I would get confused. Okay. So the first thing I'm going to do is calculate the, and I'll leave this up to you, the electric charge density, which is going to be the total charge divided by the total volume. Now, that is a little tricky because the volume of the sphere, is 4/3 pi r cubed, but you don't have a sphere. right? You have actually a difference in spheres. You have this volume minus a whole, and then divide by the charge per unit volume, right? So that's the volume density, charge volume density, and we need that. Okay, now I can do Gauss's law. This is the charge inside over epsilon naught, not the total charge, just the charge inside the sphere. I picked this so that it's easy. If everything is spherically symmetric, then the electric field should be perpendicular to the area and not changing. So my total flux is just going to be EA. And what's A? Well, it's a sphere of radius r, which is a variable, and that's fine. And we know the surface area of a sphere. Well, you should. If not, you can look it up. And that's going to be E times 4 pi r squared. That's the surface area of a sphere. Now, for the charge inside, I need this volume. So this is going to be equal to the volume, not the total, that's total volume. The volume times the charge density divided by epsilon naught. So what is that volume? Okay, well now I am going to do that. So the volume of the whole sphere, it's going to, of this sphere of radius r, is going to be 4/3 pi r cubed. That's just the radius, that's just the volume of the sphere. Then I have to subtract off this whole, so minus 4/3 pi r1 cubed. That's the total volume of this area. And if I multiply that by my density, I get the thing, the total charge. Okay, so let's put this together. So I have E, that's on E times 4 pi r squared equals the volume. I can factor out a 4/3 pi. 4/3 pi r cubed minus r1 cubed times the density, which I'll just put as rho, over epsilon naught. Okay, so that is the answer. I can just solve for the magnitude of the electric field by dividing both sides by 4 pi r squared. E equals, the 4's cancel, the pi's cancel. R, I have 1 over 3 r squared r cubed minus r1 cubed times the density over epsilon naught. And that's the magnitude of the electric field. Okay. Now you can check a couple things. You can check, one, make sure this has the same units as the electric field due to a point charge. Check that. Okay. Number two, well, once this would explode, it would keep getting giant and giant as you get further away, because it would include more charge unless you get outside the surface. Once you get outside here, now as I get a bigger r, the amount of charge doesn't change, and I should get the electric field due to a point charge. Okay, that's a 13-minute video, so maybe I'll stop or you won't watch the whole thing. And I'll send you a couple other links on Flux too that will help, hopefully. Bye.